So, hello everyone. Today we will start the second lecture of module P, that is enzyme kinetics. So, mostly in this lecture we will be discussing Michaelis Menten kinetics. So, let us revisit what we discussed in the last lecture. We discussed the basics of enzymes and their classification. So, basically enzymes are protein, they catalyzes all biochemical reactions, and we have discussed different way of classification and nomenclature of enzymes. Then how enzyme works, enzyme kinetics. So, we discussed mostly this enzyme which bind with substrate to form this enzyme substrate complex, and then further it is dissociated to enzyme and into product. So, in this way the product is formed. Now, how it works, we discuss it works like a lock and key model. Key model, and it's very, this provide the specificity, it's very specific, and binding takes place at active site of enzymes. Then further we discuss how this enzyme works. So, basically it lowers the activation energy, and once it is lowering the activation energy, rate increases. EA, activation energy, is lowering and the rate of reaction increases, but at the same time there is no change in the equilibrium, means delta G of product formation minus R T ln K. K is the equilibrium constant, so K remains same. So, there is no change in the equilibrium, but at the same time the rate of reaction is increased. To proceed further, today we will be discussing very basic of enzyme kinetics, that how we can analyze the rate of enzymatic reactions, and then further how this Michaelis-Menten kinetics equation was derived. So, as we know this, how the rate of reaction is defined here is dP upon dt, rate of product formation, or minus ds upon dt. So, minus is coming because this is a depletion of the substrate, in decrease in the substrate concentration. So, we need to know initial velocity or the rate of reaction. Then one more term will be coming, maximum velocity, that we will be referring V max, substrate concentration S, and one more parameter you will be seeing Michaelis-Menten constant Km. So, these are the parameters we are going to discuss here. So, Michaelis and Menten in 1913 built this model based on the Henry's work. The whole idea was how to explain the initial rate of enzyme catalysis reaction that depends on the substrate concentration. So, it says rate depends on the substrate concentration. So, this is very similar to the chemical reaction where it says dC upon dt is proportional to the C, and here we write the rate constant K. So, let us quickly revisit here. So, we have already discussed the enzymes and substrate. They combine like a lock and key model. This is enzyme and this is substrate. This leads to the formation of enzyme substrate complex, expressed by this reaction. Substrate enzyme, they are finding the enzyme substrate complex, and this reaction is reversible, means K1 and K minus 1 are the rate constant. Further, ES is leading to the formation of your product P, and enzyme is again released. So, initially we started with enzyme, then enzyme substrate complex, and again there is an enzyme. And what is the key here? The substrate binds at the active site of the enzyme. So, based on these concepts, these two are the rate equations, E plus S to ES, and second step is ES is converted to P plus E. So, I will write here again this E plus S, it gives rise to enzyme substrate complex, and this is K1, K minus 1, and enzyme substrate complex further leads to the formation of product and enzyme is released again. So, before we go for the kinetics, there are few assumptions. The first is negligible reverse reaction, means this step is irreversible, there is no formation of P to S, product is not converted to substrate. Now, next assumptions, in actual there can be multiple enzymes and multiple substrate, but here we are assuming there is a single enzyme substrate complex forms and that breaks into E plus P. Now, as we discussed, there are two key steps. The first one is formation of enzyme substrate complex, and second one is breakdown of enzyme substrate complex. So, S plus E they combine to form ES, and this ES is break down to the P and E. So, after knowing these equations, it is easy to write the rate equation for the same. So, if I write E plus S K1 K minus 1 ES. So, for this equation the rate equation will be d ES upon dt, this equals K1 ES minus, this is going to this direction, reverse direction, K minus 1 ES. Now, if I write the second equation, which is ES is goes to K2 E plus P. If I write dP upon dt, this will be K2 into ES, right. So, the dP upon dt is K2 into ES, and dES upon dt is K1 E into S, the forward reaction, K minus 1 ES backward reaction, and further it is also going to the K2 into ES. So, these are the two rate equations based on the given the two step reactions. Now, as we know this enzyme, we have the initial enzyme, now that is partly converted to the enzyme substrate complex. So, to account that we say there is a total enzyme concentration which was initially, that is equals to the total enzyme concentration is equals to the E, which is free enzyme available for the reaction, as well as the ES which is bound and the part of enzyme substrate complex. So, here what we have to do in the first rate equation where E was there, E will be, so basically this is basically E, and E has been replaced with E naught minus ES. So, now if you want to have this mechanistic model of this in simple enzyme kinetics, so there are two approaches. One is rapid equilibrium approach, which is linked to the Michaelis Menten equation, and second is quasi-steady state approach. So, we will be discussing both of them to derive this enzyme kinetics. So, first one is the rapid equilibrium. So, it says there is a rapid equilibrium between enzyme and substrate to form enzyme substrate complex. So, it says the equilibrium constant K, this will be equals to K minus 1 divided by K 1. So, if I write the equation once again here, it says E plus S K 1 K minus 1 E S. So, here the equilibrium constant will be K equals K minus 1 upon K 1. The same can be written in terms of concentration of the reactant and product. So, this will be equals to E S divided by E S, alright. So, in this way this is says there is a equilibrium, rapid equilibrium between enzyme and substrate to form enzyme substrate constant, and this equilibrium constant K is known as Km, that we will see. This is also called Michaelis Menten constant. So, this approach was derived by Henry, Michael and Menten, which say there is a rapid equilibrium between enzyme and substrate to form the enzyme substrate complex. So, basically it give more emphasis to the first step of enzymatic reaction. Now, you can further rearrange the same. So, it says Km is K minus 1 divided by K 1, that equals to the E S E S enzyme substrate complex. As we know now, E can be replaced by total enzyme minus E S, the enzyme bound enzyme, into S divided by E S. Now, from here we can find the expression for E S. So, E S will come out to be, if we rearrange this will be E naught into S divided by K minus 1 upon K 1 plus S, and this term is known as Michaelis Menten constant. So, now it will turn out to be E naught S divided by Km plus S. Now, if you go to the first step, if you go to the second step, it says Es is converted to E plus P, the rate constant is K2. So, if you remember, dP upon dt equals K2 into Es. So, if I put the value of Es here, so it becomes K2 E naught S upon Km plus S. Now, this term K2 into E naught, this is known as Vmax. Vmax S upon Km plus S. So, this is the typical Michaelis Menten equation, which says Km is K minus 1 upon K1 and Vmax is K2 into E naught. So, further in the subsequent slide we will see the significance of Km and Vmax and K2, but at this moment we have derived this Michaelis Menten kinetics. This is in fact known as the saturation kinetics because it reaches to the plateau. Now, we will go to the next approach, which says quasi-steady state approach. So, this was proposed by Briggs and Halden. So, what it says, the change in the intermediate concentration with respect to time is assumed to be negligible. So, what it says is we have to consider dEs upon dt is K1, K minus 1 as well as K2. So, it is not assuming the rapid equilibrium, rather it says dEs upon dt is negligible or close to 0. So, it says dEs, there is negligible change here. Now, from this equation let us write again this, it says E plus S, this gives rise to enzyme substrate complex. Forward rate constant is K1, backward rate constant is K minus 1. So, if I write dES upon dt, this will be equals to K1 forward rate E S backward minus K minus 1 ES, and further this ES is converted to E plus P. So, this further goes minus K2 into. Now, from here we have to calculate the value of ES. We have to repeat the similar exercise. So, this will be equals to ES. So, once this term tends to 0, this tends to 0. So, this becomes ES equals K1 E S divided by K minus 1 plus K2. Now, what it says again here, E will be replaced by E naught minus ES, K1 E naught minus ES to ES divided by K minus 1 plus K2. Now, if we can rearrange, so we will get the ES as E naught S divided by K minus 1 plus K2, this whole divided by K1 plus S. Now, this term here is known as, defined as Km. So, what Km is here is, Km is K minus 1 plus K2 divided by K1. So, in case of rapid equilibrium constant, what is the value of Km? Km was K minus 1 upon K1. Here it is changed as K minus 1 plus K2 upon K1. So, once this ES is known, now we can write dP upon dt is K2 into ES. So, it will become right K2 E naught S divided by Km plus S, and as we know K2 into E naught is the Vmax. So, again we end up with the similar expression of enzyme kinetics. The only difference is the expression of Km is different for both the approaches. Now, here if you just see, if you increase the substrate concentration, how the rate of reaction changes, it increases rapidly, then reaches to the plateau, and the plateau value is, the saturation value is the Vmax. And how Vmax is calculated? It depends on the Vmax is K2 into E naught. So, it depends on the what is the value of, what is the amount of enzyme present into K2, the rate constant for the second step. So, because of this, K2 is also known as the catalytic constant. So, it can be also replaced as K catalytic into E naught. Now, here as we know, this V is V max S upon Km plus S. Now, there can be different way to understand this kinetic parameter, particularly this Km and V max. One simple approach is, you assume V is V max upon 2. V is V max upon 2. If this is the V max, this is V max upon 2, and corresponding to this, whatever the S value, this is the S value is there, that is known as the Km. So, if you put here V as V max upon 2. So, I am putting V max upon 2, this is the V max S upon Km plus S. So, V max will be cancelled out. So, we will end up with 1 upon 2 equals S upon Km plus S, and if you just rearrange this, you will get Km equal to S. So, when V is equal to V max upon 2. So, in this way the Km is defined. Km is equals to the substrate concentration when rate is equals to the half of the maximum velocity. So, if you just see here, it is following a linear. So, basically this is more or less a linear range, and this is almost a straight line or saturation. Now, we can further discuss what is Michaelis Menten constant. So, as we derived, it is related with the substrate. So, it is considered as a relative measure of substrate binding affinity or the stability of enzyme substrate complex. So, if you are having a lower value of Km, it implies higher enzyme affinity to the substrate. In fact, one can calculate the catalytic efficiency of enzyme by calculating K2 upon Km or K catalytic upon Km. So, if Km value is low, what does it mean? It will have the higher value of catalytic efficiency. So, Km varies between enzyme and even for different substrate of the same enzyme. So, Km keeps varying. So, if you want to compare the performance of enzyme for different substrates, so it is easy to calculate the catalytic efficiency. So, if you calculate the catalytic efficiency, so higher the catalytic efficiency means lower value of Km, the substrate with higher catalytic efficiency are more favorable. So, what it says, the Km indicates the enzyme affinity for the substrate. Now, K2, another kinetic parameter K2 or this K catalytic constant. So, it says this is the second step, decomposition of enzyme substrate complex to give the product plus enzyme, and this is a irreversible reaction. This is the irreversible reaction with a rate constant of K2. So, K2 is known as turnover number or catalytic constant, and how we are defining the turnover number is a kinetic constant defines a number of substrate molecule converted to product per unit time per enzyme molecule. So, if you remember how the rate we are writing, rate is dP upon dt or minus ds upon dt. So, turnover number is directly linked with the rate. It says number of substrate molecule converted to product per unit time ds upon dt per enzyme molecule when enzyme is fully saturated with substrate. Now, if you remember what will be the how we define V max? V max is K2 into E naught or K2 is K catalytic into E naught. So, we can now we can say is K catalytic is the ratio of maximum velocity to the amount of initial enzyme. So, V max upon E naught is defined as K catalytic or catalytic constant. Now, what is the behavior of Michaelis Menten equation? So, there could be two cases. If I write here V equals V max S upon Km plus S. So, there can be two cases when S is much higher than Km. Second case when S is less than Km. So, when S is much higher than Km, so in the denominator we can only write V equals V max S upon S, S will be cancelled out. So, this becomes V is equal to V max, and this is a 0 order reaction. So, it says in this any substrate value is very high, catalyst becomes saturated at high substrate concentration, and as the substrate concentration is continuously increased, the reaction order of substrate reduces continuously from first order to the 0 order. So, when S is much higher than Km, the order of Michaelis Menten kinetics is a 0 order reaction. Now, you consider the second case when S is less than much less than Km. So, here we can ignore the value of S in the denominator. This becomes V max S upon Km. So, it becomes V equals V max upon Km into S. So, typically this is a first order kinetics, dC upon dt is equal to K into C. So, it is following the first order reaction. The rate of reaction is a first order if the concentration of substrate at relatively low concentration. So, here you can just see we have already written both the equations. If S is much higher, it reaches to the plateau, reaction rate reaches to plateau saturation, and when S is less, it is a linear. So, if you remember, we can go to the here. So, this is the linear and this is the saturation. When S is less, it follows the which kinetics? When S is less, it is following the first order kinetics. When S is high, it is following the 0 order kinetics. Now, we will solve a few examples to revise these concepts. The first one is an enzyme catalyzes a biochemical reaction A to B with K catalytic equals to 500 second inverse. If the final reaction velocity is 5 micromole per second and the total enzyme concentration of 40 nanomolar and the substrate concentration of 60 micromolar, determine the value of Km. Alright, so we will simply write Michaelis Menten equation V equals V max S upon Km plus S. We know V max can be written as K2 into E naught S upon Km plus S. Now, you just see all the parameters are given. K catalytic is 500 second inverse, V is given as 5 micromole per second, enzyme concentration is 40 nanomolar. So, that can be converted to micromolar, 40 into 10 to the power minus 3 micromolar, and substrate concentration S is 60 micromolar. So, all the parameters are given, we can quickly calculate the value of Km, and this will be equals to 180 micromolar concentration. Now, following this, we will see one more example here. It says the enzyme alpha amylase used in starch hydrolysis has an affinity value of 0.12 molar, and to achieve 1/4 of the maximum rate of hydrolysis. So, it says V equals V max upon 4. What you have to calculate is estimate the required starch concentration. What you have to calculate is the substrate concentration. So, it says V equals V max S upon Km plus S. So, here you can rearrange V upon V max equals S upon Km plus S. So, V upon V max is 1 by 4, Km is given affinity constant 0.12 molar. If you put the value here, we should be able to get the value of S. And if I calculate this, the value of S will be 40 millimolar. So, these are the simple examples, just you have to see what are the given parameters and what is the unknown, you need to calculate following this a simple Michaelis Menten equation. So, we will look for one more example here. It says if enzyme phosphatase has Km value of 1 into 10 to the power minus 4 mole, its substrate P nitrophenol phosphate is present at 4 into 10 to the power minus 4 mole. Then find the rate of reaction as a fraction of V max. So, you have to calculate. So, if I write the equation V equals V max S Km plus S. So, we have to write V in terms of V max. So, we can simply rearrange V upon V max S upon Km plus S. What is the value of S? S is 4 into 10 to the power minus 4 mole and Km is 1 into 10 to the power minus 4 mole. So, if I put over here, so usually 4 divided by 4 plus 1 is 5 into 10 to the power minus 4. So, the answer will be 0.8. Similar to this, we can have one more example on the same concept. Within the Michaelis Menten framework, estimate the ratio of V upon V max when S, rather than giving individual value of S and Km, the ratio of S and Km is given. So, you can put the same equation V upon V max S divided by Km plus S. S is 9 Km and this becomes 9 Km plus Km. So, this becomes 9 upon 10 or 0.9. So, in this way there can be the ratio of substrate and Michaelis Menten constant and there can be individual value of these two parameters. Now, we can see one more example here. So, what it says, at the initial rate analysis of for the reaction in solution with E naught, initial enzyme concentration of 0.10 micromolar and substrate concentration is S naught, yields the following Michaelis Menten parameters: V max 0.6 micromole per second, Km 80 micromole. Now, interestingly here enzyme follows the Briggs-Haldane mechanism. Briggs-Haldane mechanism means it is assuming the quasi-steady state, it is not assuming the rapid equilibrium state. So, if you remember in case of Briggs-Haldane mechanism, how Km is defined? Km is defined as K minus 1 plus K2 upon K1, alright. Now, what is given over here is E naught is given, E naught is 0.1 micromole, V max is 0.60 micromole per second, Km is 80 micromole and K1 is given as 2 into 10 to the power minus 6 mole inverse second inverse. So, it says 2 micro, yes, so it is 2 micromole inverse second inverse. Now, what you have to find the value of K minus 1 and K2. To find the value of K2, it is very easy. V max is K2 into E naught, E naught is given. So, this will directly give rise to the value of K2. Now, second is, once you know the value of K2, Km is given to you, K minus 1 is given to you, I can find the value of K minus 1. So, K minus 1 will be Km into K1 minus K2. Now, from here we can find the value of K2, 0.6 divided by 0.1, the K2 will be 6 second inverse. Now, I can put the value of K2 over here. So, what is the value of Km is 80, K1 is 2 minus K2 is 6. So, this will be 160 minus 6, 154. So, this is the value of K2 is 6 and K1 is K minus 1 is 154 micromole inverse second inverse. So, in this way you should be able to apply this Michaelis-Menten equation to derive or calculate the rate equations or the kinetic parameters. So, with this I will stop here. Thank you so much.